Hello, class. I want to go over a few questions from the homework, a few of the commonly asked problems. We're just going to run through this pretty quickly. Hopefully, it'll only take about 10 minutes, 5 or 10 minutes. Anyway, let's look at the first map. So the first map is showing you 1,000 to 500 millibar thickness values in meters. Okay, so we know that with a warmer atmosphere, we're going to see higher thickness values. A colder atmosphere, we're going to see lower thickness values. So if you look at this map, much higher thickness values towards the south, much lower thickness values to the north. This is just telling you that you have warmer temperatures to the south, colder temperatures to the north. What about your isobars, your surface pressure? Well, if you look, you can see where you have some low pressure systems taking place as well as some very close isobars. So what we're looking for is trying to identify baroclinic and barotropic environments. Okay, areas that are baroclinic are going to have an intersection between your isobars and your thickness value. So this is going to show you areas of convection. Barotropic environments are not going to have an intersection taking place because there are no fronts in a barotropic environment. So baroclinic, we're dealing with fronts. Barotropic, we're dealing with no fronts. So look across, let's say from South Dakota into northern Texas. You see your thickness values decreasing as we go further to the north. So there's definitely a temperature gradient as we move to the north. But look at your isobars. Your isobars are moving north to south. Okay, so there's a strong intersection taking place between your isobars and your thickness values. This is indicative of a baroclinic environment. Okay, another place that this is occurring where you have a baroclinic environment is on the west coast. Okay, very similar setup over here. This is a much larger setup with a more pronounced circulation taking place over Wyoming and Colorado. So this is going to be your main area of concern. Barotropic environments, no fronts taking place. A perfect example of this is over the southeastern United States. Very few height lines, very, very few, if any, isobars. Okay, so there's not much taking place as far as an intersection between your isobars and your thickness values. All right, so everyone did pretty well on that map. All right, let's look at this map. This is showing you 500 millibar absolute vorticity. Okay, so this is taking in both relative vorticity and planetary vorticity. Now, what you're looking for is we're talking about this trough that's taking place. Okay, the shortwave trough that is existing over eastern Texas and Louisiana. What we're trying to determine is where you're going to have decreasing planetary vorticity and increasing planetary, increasing relative, decreasing relative vorticity, and so on. And where would you expect this trough to move within the next 24 hours? All right, so anytime a parcel moves towards the equator, okay, so to the south in the northern hemisphere, we are going to be decreasing our planetary vorticity, and we are going to be increasing our relative vorticity. Just the opposite occurs as you move towards the poles, or to the north in the northern hemisphere. So as we move from B to C in this case, we are actually increasing our planetary and decreasing our relative vorticity. Okay, so from A to B, decreasing planetary, B to C, increasing planetary. A to B, increasing relative, B to C, decreasing relative. All right, so next you were supposed to identify where this trough is going to move. Okay. What you want to do in this case is find the tightest gradient around this trough. Tightest gradient appears to be right through here. And you always want to orient yourself from high to low pressure. So we know that this is a low pressure or lower height lines in this case, but we're going to be looking at this as a trough. So I basically imagine that there's a low pressure at the center to help us orient ourselves. So we can know that there's going to be higher pressure out here. We're going to orient ourselves from high to low pressure. So we go to the right of the tightest gradient, and that is where we would expect our trough to move. Tightest gradient is right through here. To the right, we would expect the trough to move towards Mississippi and Alabama in the next 24 hours. Let's say our tightest gradient was right here. It's not, but let's just say it was. Orient yourself from high to low pressure. So here's would be the high pressure, in a sense, towards the low pressure, the lower height values. All right, so to the right would be to the south. Okay, so this trough would want to continue to dig. But since this is our tightest gradient, we'd expect this trough to move to the northeast over Mississippi and Alabama. All right, let's move on to the next map. This map dealt with jet streaks. The next couple maps are going to deal with jet streak. This map, though, does not deal with a curved jet streak. This is a zonal jet streak moving from west to east. Okay, it's a very large jet streak, and we have it's a very large jet stream, and we have a very large jet streak located in the middle. All right, so remember, when we're dealing with a jet streak, we got a quadrant off our fastest wind speeds. Okay, so our fastest wind speeds are across Texas, northern Louisiana, and central Mississippi. So we're going to first divide this jet streak from left to right. Remember, you're orienting yourself with the flow. Okay, so we're flowing from west to east. So to the left would be northern Texas, southern Oklahoma, and Arkansas. To the right would be southern Texas, southern Louisiana, southern Mississippi. All right, then we're going to also divide our jet streak from entrance to exit or front to rear. Okay, so we'd cut it right through the middle. All right, I also tend to extend my jet streak quadrants out a little further just due to discrepancies in the model or inconsistencies. All right, but these are our fastest winds through this area. So let's look for areas of divergence and areas of convergence. Okay, areas where we'd see uplift and areas where we'd see sinking air. Okay, so we know that in the right rear quadrant and the left front quadrant, we have divergence. So right rear quadrant, left front quadrant, we are going to see divergence. In the right front quadrant and the left rear quadrant, we are going to see convergence or sinking air. All right, so that is how you would break down this jet streak. Let's move on to the next one. All right, now we are dealing with a curved jet streak. We would consider this to be a cyclonic jet streak due to the flow around the trough. Okay, the flow is cyclonic. All right, so here is our jet streak. You can see a very strong corridor of very fast winds. All right, you see very, very fast winds in the middle, but we're going to extend this out a little further. And I'm actually going to probably go back and give everyone probably 5 bonus points because I should have specified on this question to extend your jet streak out further than just right here in the main corridor. I'd actually extend this out a little bit further just because these are very fast winds throughout, and it's a curved jet streak, so you want to get that flow in there as well. So I'm going to go back and give probably 5 bonus points to everyone just because I feel like this was a poorly worded question. And I should have described it a little bit better because one of your answers dealt with Oklahoma. And if you just did your quadrants with your fastest winds, then it would be very hard to get Oklahoma in there. So I apologize about that. I'll go back and give people credit where credit is due. I'm going to give everyone bonus points for that. But let's just go through real quick and talk about how we would extend this jet streak out. All right, so let's make our jet streak right through here. Okay, so we're going to extend it out a little bit further than our fastest wind. So let's extend it out to about here and to about here in southeast Arizona. All right, this is going to give us a bigger picture of what's going to actually be taking place. Okay, so we have very fast winds throughout. Now, remember that this is a curved jet streak. Okay, so we're going to still have our divergence in the right rear and the left front and our convergence in the left rear and the right front. But when we're dealing with positive vorticity advection and negative vorticity advection, remember we got to take into effect curvature. Okay, so since this is a cyclonically flowing jet streak, that's poorly worded, but there's cyclonic flow, okay, around this trough. Okay, so it's going to be cyclonic. Well, we also need to look at the shear vorticity. So we have cyclonic curvature vorticity, and on the left side of the jet streak, we also have cyclonic shear vorticity. All right, so that's going to maximize the left side of this jet streak. Well, on the right side, we still have cyclonic curvature vorticity, but now we have negative shear vorticity. All right, so you actually get a minimum on the right side of the jet streak. So when we're dealing with positive and negative vorticity, we're really concerned about the left side, okay? So we would expect to see positive vorticity advection in the same areas we would see divergence, and convergence in this, and negative vorticity advection in the same areas we'd see convergence. All right. Remember, we're concerned about the left side because the right side is canceled out. So we'd see negative vorticity advection back here, positive vorticity advection up here into northern Texas and western Oklahoma. All right. So I apologize. There's probably a little bit of confusion on that question based on the size of the jet streak. I should have told you in this instance to expand your jet streak into southeastern Arizona all the way up into, Texas-Oklahoma border. So I apologize about that. So let's move forward. All right. Now, this map, this one was dealing with isotropic analysis. All right. So what we're looking for here is we are looking for advection of your mixing ratio. Okay, where your mixing ratio is going to move to. So one of the questions actually asked you at what area or what isotropic surface is shown on this map. Well, if you look at the top left, you can see it's going to tell you the isotropic surface that we're dealing with. So we're dealing with 296 Kelvin is our isotropic surface. And if you look back in your notes, you would have seen that that is dealing with spring. All right, so on this map, you are looking at colors. You're looking at color ranges. Your brightest colors are going to be your highest mixing ratio, where you have the most amount of moisture. Your darker greens are going to be the lower mixing ratio, okay, where there's not much moisture taking place. So this is very similar to looking at warm and cold air advection, okay, except we're dealing with mixing ratios. Where are these mixing ratios going to be advected to? Well, look at the winds coming off the Gulf of Mexico. All the winds coming off the Gulf of Mexico are to the south. Okay, we have our highest mixing ratios right in here. So we are going to be advecting higher mixing ratios into, eastern Texas, Louisiana, Mississippi, Arkansas, and so on. Well, in other areas, just the opposite's taking place. If you look further north into the Great Plains, you actually see a northerly wind, and it's going to be advecting lower mixing ratios into parts of Kansas, Nebraska, parts of Oklahoma, parts of northern Texas, so on and so forth. So what you're looking for here is where advection is taking place and where you're moving your higher mixing ratios, where those higher mixing ratios are moving into, where your lower mixing ratio is moving into. All right, let's look at this cross-section analysis real quick. So your dashed yellow lines are your equivalent potential temperature. So what the temperature would be of a parcel of air if all of the water was condensed out and it was lowered to 1,000 millibars, okay? Your solid red lines are your isotropes, and your solid green lines are your mixing ratio. Your, which ones am I missing? Solid blue is your wet bulb zero. One thing that when you're dealing with a cross-section that you want to get through your head real quickly, and it'll make things a lot easier, is your isotropes, your red lines, and your equivalent potential temperature, your dashed yellow lines, are always going to slope up towards cooler air. Okay, so they're going to slope up towards cooler air, because if you were to lower that parcel back down to the surface, that is the temperature it's going to give you. So if you can remember that you're always going to slope up towards cooler air, slope down towards warmer air, it's going to make things a lot easier when looking at a cross-section analysis. All right, so 72233 is indicating Slidell, Louisiana, and then 72645 is going to be Green Bay. All right, so this cross-section is taken from Slidell to Green Bay, and we're looking to identify where our moisture is decreasing, where we're going to have a cold front, so on and so forth. So let's look first at your mixing ratio. All right, so those are our solid green lines. So if you look furthest to the south, okay, look over Slidell, we have a mixing ratio of 8. Okay, and if we move to the north, we're going to decrease. We're at 6, we're at 4, we're at 2. Okay, so our mixing ratio is decreasing as we move further to the north, which makes sense because we're moving further and further away from our moisture source, the Gulf of Mexico. All right, so our mixing ratio is definitely going to be the highest towards Slidell. All right, so now let's look, since we're kind of on the same topic, let's look at your wet bulb temperature, your wet bulb zero line. Here is your wet bulb zero line, okay? So So if we evaporated all of the water, we could basically get our temperature of a parcel down to 0 degrees at this level, okay? So above this level, our air, if we evaporated all the water out of it, could be lowered down to 0 degrees. Okay, below it, it's going to be warmer than 0 degrees Celsius, so we're still above freezing. So that's a kind of an easy way to think of it. You evaporate all the air out. This is going to be the temperature of the parcel the air could be if you evaporated all the water out. So this is your wet bulb 0. So this really helps us identify where we're going to get different types of precipitation. So an easy way to remember this is if your wet bulb 0 is high up in the atmosphere, you could expect that you're going to have rain. Okay, the reason I say that is because everything below here, if all the water was evaporated out below this blue line, we'd still be above freezing. So our precipitation at the surface is still going to be rain if we were forecasted to have rain. I'm sorry if you can hear my dog in the background. He's drinking water. Anyway, if you look at farther to the north, our wet bulb 0 is actually at the surface or below. So if we evaporated all of the water out, we would get well below freezing. So we could expect if any precipitation fell to the north, we would see snow. Obviously, we'd have to do a lot more investigation, but we could assume snow would be taking place here. So let's look at our temperatures, or let's look at our theta. So now let's examine our theta E and our theta values. So we know that our theta E and our theta values should rise towards cooler air, okay? So rise towards cooler air. So let's just say we followed up one of these lines. Let's look at 290 degrees Kelvin, okay, with our theta value. We follow 290 Kelvin up as we move to the north, okay? So it's getting higher and higher into the atmosphere. So if we brought that down, if we brought that parcel down to the surface, we could reach 290 degrees Kelvin. That's why it is going up as we get towards or move towards cooler air. So we see our theta and our theta E lines are both moving up as we go into cooler air. So we know something is taking place here. We see our moisture values decreasing as we move north. We see our wet bulb 0 getting close to the surface as we move north. And we're seeing our theta E and theta values moving up towards cooler air as we move to the north. So we know a front is taking place. Now, to identify a front, you're looking for tightly packed isotropes. Okay, so where these lines are closely compacted together at the surface, that's going to indicate where your front is located. So your front is located in this area right here. Okay, our lines are sloping up towards the colder air, so we know that this air back here is extremely cold. And look how tightly packed our theta E and theta values get over station 72327. They get very tightly compact. So this would be where our front is taking place. Now let's talk about this feature located in the upper atmosphere, the upper troposphere. What is this feature right here? Well, let's look at our theta E and theta values. So we see that they are sloping up towards colder air on both sides of this feature. So this is indicating that the center of this feature is actually pretty warm. So where could we get warm air high up in the atmosphere? Well, we're getting this warm air actually from the stratosphere. Remember, the stratosphere increases with height. The temperature increases with height. So we're actually getting a tropopause fold taking place, where we're getting temperatures from the stratosphere being pulled down into the upper troposphere. All right, that is why we're seeing warm temperatures at the center of this feature right here. Okay, so there's high static stability. There's very little moisture. There's no moisture, really. That's why we don't see any moisture or any weather taking place in the stratosphere, because we have removed all of our moisture by the time we get up to that height. So this is a tropopause fold taking place. All right, so please ask me questions. I know isotropic analysis and cross-section analysis can be a lot going on, can be very overwhelming. I apologize if I was a little scatterbrained through this. I made this video at home. I'm actually going out of town in an hour, so try to make this real quick before I left. There are a lot of things going on in the background, so I apologize. So if I said something that didn't make sense, or got something backwards, please let me know. I'll be happy to fix it. I hope this helps you, and please feel free to ask me any questions that you might have. Thanks.